These 4 words, there's a reason why in a textbook this can take up to 4 sections. It's because these are 4 essential steps of doing a problem. So first, you need to be able to figure out, oh look, it's a word problem. It describes a situation. How do I model this situation mathematically? So that's what representing is about. Now, planning, well, of course, you need to have some idea of how you're going to do this problem. You get from point A, which is what you start with, to point B, which is where you want to be, i.e. the answer you're looking for. Now, yes, there are plenty of famous quotes such as the best laid plans of mice and men and plans never survive contact with the enemy, and of course President Eisenhower's quote of, I have found that plans are useless but planning is essential. But you need to plan anyway, as Eisenhower did say. So you need to have some plan of getting from where you begin with, what you're given, to the solution you want. And then you need to reason it out. You need to actually do the problem. And of course employ sound logic throughout it. Afterward, you need to reflect, which is a glorified way of saying check your answer. Now, when you're representing things, well, often you will find that problems use a coordinate system, especially in, say, data management, or when you're looking for trends in general. Now, a coordinate system is what happens when you have an x-axis, a horizontal number line. So say from 0 to 10 or something. And then you have a vertical axis, which is a vertical number line. It's also from 0 to, say, 10 or whatever you want it to be. Now, what happens here? Well, there's a grid that you don't usually draw out. But if you do this on graph paper, the grid is naturally there. And if you plot dots in here, you plot points of data, you can find if there's a trend or not, and whether the trend is strong or weak. Now, the origin is 0, 0. It is commonly simply labeled as O. Usually, when you label the 0, you only label 1, 0 instead of labeling both when you draw a coordinate system. Why? It's because usually you have the axes drawn something like this. Different areas have different conventions over whether or not the negative ends also need to have arrows to denote that they, in theory, go on forever. Now, if you graph data on the coordinate system, well, you've probably done it with graph paper before. Graph paper, i.e. the ones with the square grids. Technically, if you did, say, a bar graph, that's not a coordinate system graph. It's a coordinate system graph if you do, say, a line graph or a scatter plot. Because on a bar graph, the horizontal axis doesn't have meaning that's quantitative. Whereas on a scatter plot or line graph, usually the horizontal axis does. Bar graphs are, for the most part, considered qualitative. Now, admittedly, histograms technically are quantitative, but they do separate the data into qualitative bins of information. Histograms are basically bar graphs where all the bars are joined together at the edges because they're ranges, they're bins of data. If you're on the edge, you're in this bin. If you're on the other edge, you're in that bin, and so on. And if you're in the middle of a bin, of course you're in that bin. Now, people's heights are commonly listed by histograms, whereas, say, color preferences are by bar graphs. What's the difference? Because heights are a continuous range of variables, or in this case, numbers. Whereas discrete variables, like favorite color, are categorical. Now, let's do some examples of how we use a coordinate system. So we should label the scale, which we determine after reading the problem. So find 5 points with whole number coordinates that could be the final vertex. So anything that's not on a straight line through here can potentially be the final vertex. So say we have, well, -4, 5. Or does 0, 0 work? Yes, because the line through these 2 points does not pass through 0, 0. Comma, comma. And say, well, if we want to be lazy, we could write 0, 3 and 3, 0. But teachers tend to not appreciate overly joking, even if it is valid. It tends to annoy them. And annoying your teacher is not sound strategy. So then we could do, say, 5, -2 or something. And of course, -2, -4. Now, what happens if we want this to be an isosceles triangle? Well, we could have this be the base, in which case the points would be anywhere along this diagonal through 0, 0. 1, 1, for example. Or we could have this be one of the legs, in which case it could be over here, which would be 4, 1. Or it could be up here, so 1, 4. Or it could be down here or down here. So -2, -5. And over here would be -5, -2. All right. So if we consider how to do these problems and then act, that fills the planning part of this section, this very condensed section. Now, for example, how many times can 5 go into 1,000? Why? Because they want 1 and 1,000 inclusive. So the number of times that 5 can fully fit inside 1,000 is the total number of numbers that apply. So 1,000 divided by 5 equals 200 numbers. And divisible by 7, well, 1,000 divided by 7 is equal to, we know that there's going to be a remainder. Why? Okay, 490 is 70 times 7. So 980 is, well, twice of 70 times 7, which is 140. And then what about the last 20? Well, that 20 is a little under 3 times 7, which is 21. So that's 142, and then 6/7. But this gives us this many numbers. This is an arrow sign instead of an equal sign, because if we wrote equals, then it would be 142 6/7. And that then leads to 142 numbers. But we decided to be lazy in our writing. Of course, depending on the teacher, they might not let you get away with this. So what about both 5 and 7? Well, 1,000 divided by 35, which is the lowest common multiple of 5 and 7, is equal to 1,000 divided by 35 equals approximately 28.6. So this leads to 28 numbers. All right. So what next? Well, example 3. Yeah, I know, predictable. But we're supposed to calculate using appropriate tools to help us solve these problems. So these appropriate tools could be calculators, or it could just be our brains. So let's calculate. All right, -3/4 times 33 over 100 Now, we notice that we can cancel some things out. For example, we can cancel this to 1, we can cancel this to 11, and that cancels this twice. 144 is 12 squared. That's 3 times 4 times 3 times 4, which means this cancels out to 4 times 4, because we canceled 2 3's. And that means 16. And we cancel this with this up here, which is 4 times 16. So 4, we cancel this again, and this becomes 25. So what do we have left? Well, we can also cancel out the minus signs because, well, there are 2 of them. There's an even number of them. So this leaves us with 3 over 4 times, we could have canceled this 4 instead, but whatever. So 100 down here and 11 up here times 2 times 4 is equal to 8, and 8 plus 3 is 11. So when we flip, that would mean 4 over 11. And this means, once again, this cancels down to 25, and these 2 are canceled completely to 1 and 1. So this comes out to 1 over 25. And what about this next question? So here we have 2 to the 100th times 10 to the negative 200th and times 50 to the 100th power. Now, this is equal to 2 times 50 to the 100th power times 10 to the 2 to the negative 100th power. This you can't use your calculator for because of the number of digits that calculators can tolerate, which is not this much. So this is 100 to the 100th times 100 to the negative 100th, which means equals 1. This all cancels out. Alright, next we have nothing. Yeah, this section we have slightly less than the standard amount of examples, which is nice.